is how you indeed take these very small energy increments that you get from the magnetic dipole related to the oscillation of the electric dipole, how you can build them up, how you can transfer that into the lattice so you get local, very high energy. Now, you're working on this and you probably have an answer which I didn't understand. But that's the critical feature, and this, I think this whole model is very, very interesting.
Okay, I don't want to show
Those comments, I think, should elicit a detailed private discussion in the interest of time. Dr. Violante, briefly, please.
The question is, strong fields are created in condensed matter also when we have excitons like plasmons.
Excuse me, I can't hear you.
In condensed matter, we have also strong electric fields when we have plasmons. Have you considered this in your calculations or not?
No, and probably one shouldn't bother, because in plasma installations, the electric field gradients, as I say, probably 10 to the times less than we have here. As we have difficulties even here, that there is no way to do it with plasma.
Thank you.
Thank you very much. Our next presentation is our standby presentation by Dr. Vigier from Paris. The title is Interpretation of Cold Fusion in Terms of New Bohr Orbits Resulting from Spin Orbit, Spin-Spin and Spin Orbit Couplings and External Magnetic Fields.
Okay, well, my talk in a sense is related with Dr. Kucherov's speech. And I make the question, the question we are all facing, of course, is that we are sitting in front of a certain number of facts, namely unexplained excess energy, creation of observation of various nuclear reactions in palladium and nickel and so on, new effects like sonoluminescence and so on. And we couldn't agree on, we still don't agree on where the source of that energy momentum conservation violation is coming from. So until we provide an explanation, one can understand that we'll be more or less in trouble, even if we present practically proofs of such violations, because these experiments depend on a lot of parameters, and it's quite possible that we have forgotten some of them. So what we should look for is for given a specific proof of a model, and what is a type of new phenomena which allows hydrogen or deuterium to give excess energy when embedded into metals. So, all right. I'm going to try to risk my head on a definite experiment with a definite prediction, a little bit outside the field, namely to explain what is new when you put hydrogen or deuterium into metals, and where does a new energy come from. Now, this is no story. Of course, you can have two types of explanations. You can look for things like phonon lasers and so on, collective properties inside the metal as a source of the energy. I don't believe that. Or you must look for some new type of interaction. And if so, if there is a new type of interaction, then you must prove that it exists. Now, before we go to a new source of interaction, I'd rather go into conventional sources of interactions, namely the use of spin-spin and spin-orbit coupling interactions, which appear when you put precisely hydrogen or deuterium in a metal, because it orients the spin, and you add to the Coulomb field spin-spin and spin-orbit couplings. Now, I don't claim any priority for that. It's an old discussion. First, there was a violent discussion a long time ago between Pauli and Bohr. Bohr said, but what about those spin-spin and spin-orbit couplings? And then Pauli answered, there's no such thing as motions of the electrons in the hydrogen atom, so there's no need to introduce those hidden parameters into the model. Of course, the Pauli equation gives you a spin, but the question is whether you must modify or not the Bohr model by adding these new types of couplings. And of course, these couplings, Bohr remarked that these couplings are difficult to detect because in free space, the spin of the proton and electron are oriented at random. So it's very difficult, and so they cancel in general. So it's very difficult to detect. However, a lot of strange phenomena have been observed. And I'm going to, for example, when you shoot very high energy discharges in deuterium, then you see flows of neutrons appearing. That was a famous experiment of Löschtel-Hultgren, who shot 500,000 ampere into heavy water and got rupture of the conductivity in that curve, and a fantastic flow of neutrons. So what I'm going to discuss now is a model of spin-spin and spin coupling within the frame of ordinary quantum mechanics, and show that it can give you the new energy. As you know, that's the Pauli equation. It's well known. In fact, I have used both the Pauli equation and the Feynman-Gellman equation, but this gives practically the same effects. So here's the new Bohr orbits, and in both cases, one needs a proof of the new process in terms of a yes-no experiment. Unless we produce a proof that in specific acceptable conditions and in relation with conventional quantum mechanics, nobody is, I think, is going to buy easily the new technology. In fact, I have the impression, since I followed some of these conferences, that we are witnessing the birth of a new technology, but still we don't understand exactly what we are doing. Well, it's an old story. When Napoleon wanted to go invade England, Papin proposed a steam machine to cross a channel, and Napoleon said, "Oh, but everybody knows that you can only use oars or wind, and everything else is just junk." Well, of course, a lot of the establishment reacts in that way. So to convince these people, we'll have to produce something. So let's try and make definite predictions which can be tested in the lab, and if possible, with the simplest possible technology. So my proposal is to introduce spin-spin and spin-orbit couplings, first in the hydrogen atom, and as you will see, it just gives you a very small displacement of the levels. You can't get new energy directly from proton plus electron, but you can get new energy from electron plus 2 protons. A picture like this. So I'm going to calculate the Bohr orbits of the H2 plus and D2 plus within, placed within an external magnetic field. That can be in a cathode, or that can be in an external strong magnetic field, half a Tesla or something like that. And then the prediction is going to be that you're going to have observed new Bohr orbits. And this can be tested. So I'm ready to put my head on the chopper and see if they come or not. At least if they don't appear, if those lines don't appear, then you can say that this interpretation is wrong. Because the trouble with interpretations is that they're often so flexible, it's hard to push them into a corner. So I'll try to go myself in the corner and see what happens. So the quantum theory of a model like that is very simple. Of course, you can use the Bohr, the Oppenheimer technique, or you can use the old quantum series, an integer number of wavelengths around a stable orbit. So let's stay exactly within the frame of quantum mechanics and just add spin-spin and spin-orbit couplings to the model. All right, so that's a paper. It's just appeared in PLA, so I'll pass very rapidly. You just write the Hamiltonian, you write the new potential, and you see the new, it's in an external magnetic field, so you see new terms in 1/R3 and so on appearing in the Hamiltonian, and this amounts to put in the Bohr model a new potential, which is a function of the distance. So I'm just doing what any student in quantum mechanics does. I'm going to try to calculate the orbits. Well, it's a rather difficult task. Took some time, but all right. I'll pass because the thing I think is just published. In fact, I have tables there showing the new levels. Well, I have no time, so I'll go pass. And the conclusion is that there is a distortion of the levels due to the proton-electron spin-spin and spin-orbit coupling, but the displacements are rather small. But, of course, putting hydrogen in a strong external magnetic field, that thing should be testable. Namely, you could see the displacement of the levels. So that's the first possible experiment to see whether there's a displacement of the levels under a magnetic field. These are the table of the new level associated with the quantum numbers. So that's not a difficult experiment to make. But what is more interesting is that's the last table of the new levels. Now, what is more interesting will be to work with D2 plus and H2 plus. That's one of the problems we have to face. I mean, is it a nuclear phenomena or is it something else? Well, if it is a nuclear phenomena, it works with deuterium, but it shouldn't work with hydrogen. So if it's not, if it's something else, then what is it? So my point, it's just a conventional electromagnetic interaction when you polarize the spins inside a special experimental setup. So the model is very simple. That is the model. Put the electron in the middle, the external magnetic field. Sorry, I forgot to draw it. You put the external magnetic field and, sorry. And you have an electron in the middle, the two protons on both sides, and the whole system rotates. And I can show that but that's a rather too long point, but I can give the details to anybody interested, that it's a stable possible configuration within metal, where you have a cloud of electrons and lattice protons. And so this is a possible new phase of hydrogen, of H2 plus or D2 plus inside a metal. So, okay, so you just apply quantum mechanics to that story. You write down the levels. The calculation is a bit longer than in the case of proton and electron, and you pick up a new Bohr orbits. Now, evidently, since it's now the protons which are rotating around the center of mass, while the electron oscillates around the center of mass, then the levels are much more energetic, and instead of having electron-volt transitions, you have kilo-electron-volt transitions. So this is a source of energy, if it's true, if it's confirmed by experiment. And so my proposal is that one should do that experiment. So there is where I chop my head. We have calculated the levels by two different methods, the old methods of Bohr and de Broglie, an integer number of proton wavelengths along the circular orbit, or the Born-Oppenheimer method. And there you are, there is the predicted values here. So, point is it true or isn't it true? So, of course, I'm looking for people to do the experiments. I hope somebody will be interested enough to do the experiment and to see if Party was right to say that such thing did not exist. Well, I have added spin, and spin orbit coupling to the Coulomb field. And of course, when the two protons on both sides repel and they're attracted to the electron in between, so you have a modified potential and you have modified Bohr orbits. That is not mysterious. So the experiment can be made. What you have is to prepare D2 plus or H2 plus. Everybody knows how to do that. You put that in a condition where it's submitted to an external field which orients their spins, and you put a germanium detector or something else to detect the soft X-rays, and this yields a number of lines. I must say that, but I have no time to discuss that some experiments have been done which have seen these Bohr orbits. Of course, you have to extract them from a background. But that has been done, for example, by a group of Spark and other people in Los Alamos with deuterium, and they had observed some of these lines, and lo and behold, some of them coincide with my predictions there. But that's not a good proof, because the experiment was not done to do that. So let's try. I'm looking for somebody who wants to do the experiment and see the new Bohr orbits. Now, once this is done, then of course a lot of interesting consequences follow. Because the new tight state, well, let's take the H2 plus, D2 plus. The H2 plus is going practically to behave like a proton with a double mass. All right. These tight particles can evidently, first you can have tunneling, and that would explain the new isotopes observed within the metals. B, such particles, such molecules, if you want, can now combine with nucleus and interfere with part of them, like the people here have said. You can have even three-body interactions. I was thinking of Yamaguchi's experiments in that way. You can even imagine that such a tight molecule can combine with lithium to give alphas. The proposal in that direction has been made here. What I'm claiming is, if this is true, then there's no need to introduce any fantastic new concept into nuclear physics. One of the things which worried me from the beginning is that we thought we knew everything related to nuclear phenomena, just 1 minute, related to the observed range of energies. And so how come that something so strange suddenly appears in an energy domain which we had already expressed? Of course, there are huge important theoretical consequences. For example, I think it supports the point of view of Einstein, Broglie, and other people that but that was also Barrett's argument. Really, the father of this model, unfortunately died. I think he should be sitting among us. He was a personal friend of mine. I think this is going to, if this is true, this tells you that magnetic dipole, electromagnetic dipoles or quadrupoles can, in a sense, behave like nuclear forces, because the 1/r³ force is much more important than the usual Coulomb field, and it's just in the right range of magnitude. So this might be the first step of a new quantum chemistry, and I'm sorry to contradict the father of this meeting, namely Professor Fleischmann. Maybe quantum mechanics is perfectly okay and explains the new phenomena. You're just putting matter into a special situation where spin-spin and spin-orbit couplings appear. The consequences of spin-spin and spin-orbit coupling appear in brutal light. Thank you.
Passell?
Yes, question. Do you think this new
Sorry, I'm a bit deaf.
D2 plus is the catalyst for all these nuclear reactions where the real heat is coming from? Or do you expect any heat, excess heat from the production of D2 plus? and H2 plus.
Well, I expect there will be a mixture. You see, we interpret the nuclear forces with various new heavy mesons, right? I don't know the exact number this day. But this means you have to add something new to the story, namely the dipole-dipole, dipole-quadrupole interactions. And by the way, the model predicts supports some of the things which Kucherov have said this morning.
Well, the reason I ask the question is that I don't anticipate very much energy coming from a few kilovolts per hydrogen atom. I expect a lot of energy coming from nuclear reactions that particular thing may have triggered or catalyzed. That's the point. Because you do not have new energy source with a few kilovolts per atom.
Yeah, but you have to explain, and well, maybe two different phenomena. You have excess energy with deuterium and with hydrogen. If you have I don't understand how you explain excess energy coming from hydrogen.
Let us.
But the Coulomb barrier cannot be superseded or say something fantastic, new nuclear force.
Scott Shrub, NRL. I was curious if you thought about the implications to other atoms. The implications to other atoms, the boundary conditions of atomic wave functions close into the nucleus are always taken from Bohr orbit conditions. Your new Bohr orbits suggest that there would be new conditions that would be necessary, and in principle, a whole new set of states.
But what I'm saying is that this new type, the D2 plus or H2 plus, practically behaves now like the nucleus. The distance is so small.
Yes,
and so you have it goes above through the tunnels to the Coulomb barrier. And then it glues to the ordinary atoms, and we don't know what happened there.
I understand that. I'm asking the question of you've attempted to explain something, and I'm asking the question of does it unexplain or other possibilities? I mean, there are other implications to your theory that go beyond just hydrogen.
Yeah.
And I was curious if you wanted to comment on that or if you thought about that.
I thought about it, but I'm afraid to speak. This is already a bit, I've already crossed some forbidden barriers.
If you're afraid to speak,
But
I'll
I'm
say
ready
one
to
again.
discuss it privately with you.
Let's go on, please.
I'm already sticking my head with a definite numerical prediction of things you should observe in a definite experiment.
George?
George Lyle, University of Illinois. To put this in perspective, could you comment on how your tight orbit atoms compare with Randall Mills, hydrinos, with Floor's atoms? What's the difference between?
Well, of course, there's a similarity of this with what Professor Dufour has said, and Mills. Mills also predicts new type orbits and the quantum numbers corresponding to these new type or deep orbits. But he has something which I cannot swallow. Namely, he says that the electron around the nucleus is not a particle, it's a shell. Now, this is against quantum scattering theory. When you scatter, you make scattering on an atom, everything tells you that the orbital electrons behave practically like a point. So that's why I wouldn't buy Mills' new table. But of course, I wouldn't be surprised at all if you got good results, because the conclusion of his model, I think it's wrong. I'm not sure. I asked him the question about the scattering. He said he would write to me and publish a thing in PLA, but I never received the letter, so I suppose he has some trouble with scattering. But if not, it's the same basic idea, of course.
It's a very important question, but let me move on. I know as scientists, we're more interested in ideas than lunch, but there's a limit. Next, please.
I'm Professor Pappas of Technical University of Athens. I think, Professor Vigier, you have gone halfway unless you didn't want to go over your forbidden barriers. You mentioned dipole interactions, quadrupole interactions, spin-to-spin interactions, and spin-orbit interactions. The spin-orbit and the spin-spin interactions are equivalent to current interactions, and the quadrupole interactions, dipole interactions in the nucleus. We're familiar with the older model of Parsons of the nucleus, and the electron, represent the electron as a ring current, and the proton as a ring current. Then the nuclear forces could be easily seen as, the way you said it, dipole and quadrupole interactions there. I think to maintain the view and to stay on classical quantum mechanics perhaps is not so wise, because quantum mechanics as that there could be replaced easily by classical electrodynamics and standing waves, the way a ring electrical current would produce. And in this way, there are many models that already existed. I don't think it's a hidden barrier. It is a model of Bostic. It goes all the way into even to quarks to describe them in terms of classical electrodynamics and electrical currents. That is, elementary particles distributed as electrical currents around the nucleus, as you said. Also, the proton or the proton would be just a similarly current, and the proton can be gradually excited in various excited states so that can absorb ordinary electromagnetic energy. Also, there is extended literature by Bill Lucas, David Berkman, and others.
Thank you for your comment.
Thank you very much.
Very briefly, please.
Okay, so you quote an experiment where some people get a large amount of neutrons, 10 to 12, when applying current of the order 5,000 ampere per square centimeter. But this is a range close of pinching effect. How you can separate about the tube?
Oh, well, then I'm going to stick my head out again. My answer is this implies that the particle, the electron, has a real physical dipole moment. Namely, the charge is extended around the center of charge, and this center oscillates around the center of mass. And by the way, there are recent publications. I published a review paper in PLA showing that in that case, in straight lines, this thing does not radiate, or it doesn't radiate in a Bohr orbit. Now, to answer your point there, you see, of course, I'm sticking too much my head. If the photon has a rest mass, then of course you have simultaneous existence of longitudinal forces and transverse Maxwell waves, and then you have a longitudinal Lorentz forces along the current. So when you shoot a current into a conductor, the electrons repel along the line of the conductor, and that's exactly what the Ampere experiments a long time ago, or this Lochte-Holtgraven experiment showed. And then, of course, when you push together the heavy water, it splits into things. Then you produce this Coulomb effect and the flow of neutrons.
May I interrupt? This is a prolonged discussion, which
I'm sorry, but
no, sorry. Yeah,
that's outside the field.
Thank you for the stimulating talk. Appreciate the patience of the audience, and Dr. Kim from Purdue, who's going to give us the final presentation on role of continuum electrons and condensed matter mechanisms in ultra-low energy nuclear reactions.
I took up this for you to wake up and don't go to lunch before this talk is end. Instead, I had a lot of questions, but I couldn't ask because that will eat up my time. I will talk about problem with the conventional theory, and I was hoping that Doug Morrison would be here, but because of this delay, I think he probably wants to run. I'll be talking about all these. Some of them are new concepts, and some of them are some time ago. And eventually I'll come to my interpretation of Kasagi's experiment, which he'll be talking again this afternoon. As a way of introduction, let me show you this view graph. There are maybe more than 6 miracles after this conference, but at least those well-known things we have to understand. And most important one is the gamma effect cancellation. This is the key to all of that. So I will address this part mostly. Now, if you look at the conventional formula, it's essentially a semi-classical formula. And I have shown some textbook derivation, and eventually you end up with this gamma factor. And if you look at some of the data, Utari, let's say DDPT data, it works very well until you come to 10 kV. And some of the early experiment a few years ago showed some deviation, and those are attributed to the about 25 electron volt electron screening. And as we saw a few days ago, Kasagi had this new data, and this is very striking because we did not yet expect such a big enhancement, which is good news for cold fusion. If you take electron screening effect into this formula and replace the relative energy between deuterium by this replacement, then you can calculate the new gamma factor. For instance, at room temperature, it will be something like that. And of course, this doesn't make sense because 0 is 0. Of course, if you put like a hydrogen electron screening time, you end up with a more reasonable number, but still very small. And if you take electron distribution in the metal as a Thomas Fermi model, then you can increase this to this one. But yet, still, we are too short of these initial things, because these may be now modified, but it's impossible to get this level with standard model. And that's where all the theoretical conditions come from. Now, if you had a Kasagi's type thing, you can go up to 10 to the minus 18, which is larger than initial frame of a fraction home. Now, well, this is, we don't need that, but the early days, Leggett Bain had this paper published, and claim that there is an upper limit, upper bound to the penetration factor, conventional penetration factor, and then another factor of 60, and you would not get more than that. But we have shown that that only applies to bound anybody system. If system is not bound, for instance, the electron is in a continuum, you cannot apply this criteria. And there are other models which is exception. So this statement is not absolute. Only applies to particular system. So there are hope for improving it. First attempt we tried to improve was to do the quantum scattering theory derivation of the cross-section. And we used rigorous optical theorem to derive new formula. And after certain parameterization, we ended up with a formula of this type. Now this is a conventional gamma factor, and we gain so-called enhancement effect, which is completely quantum effect. You can get this semi-classical approximation. And this is a property that if interaction range inverse goes to 0 or interaction range goes to large, then this factor becomes gamma factor with opposite sign, so that you can have a gamma factor cancellation. Now, fact that can occur is very important because even if this component is extremely small, once you start canceling gamma factor, it has an enormous effect. For instance, if you have this in the form factor, there are small component which is longer range effective interaction, then this can occur, this cancellation. So that's one improvement we made. And if you take this seriously and ask what you need to cancel gamma factor, then those are factors you need. And the range you need to do that is order of 1,000 terms, or 10 to the minus 2 action. So we're saying that original gamma factor can be modified if you can have a mechanism which gives long-range interaction, imaginary part of elastic amplitude. One example of that is so-called halo nuclear state. We have shown in this paper that if you have excited halo nuclei, which I'll explain in a minute, then that is final product has not the ground state, but in the excited state, which is very loosely bound neutron state, then you can have this kind of cancellation. And there are those halo nuclei known for lighter atoms, lighter nuclei. For instance, there is excited states. Barium 11 has a 1 neutron halo state, which is excited state. So our prediction is that if you're doing like a DP reaction to reach this nuclei, then cross-section is enormously enhanced. This can be tested by experiment. And now the question is, does the palladium have such state? We don't know. If you look at what Yan was showing, lots and lots of state in palladium, and if any one of them happens to be neutron halo state, then it can enhance cross-section. We do not know whether that is happening or not, but eventually you can test that. Okay, now that's what I call halo nuclear state fusion, and that may or may not be occurring. But definitely it's not the conventional gamma factor form. Now I turn to so-called continuum electron catalyzed nuclear fusion. This is a drastically different situation from gamma factor. Gamma factor is essentially having bound or some conduction type electron in the metal, whereas what we are proposing here is that if there are not free, but unbound electron in a metal or free space, like here, this is in a free space, one has to solve three-body equation to see what kind of Coulomb penetration factor you can get. Okay? And one has to solve this equation in a continuum. All of three particles is not bound. So one has to solve it. But if we find out that this type of reaction can cancel gamma factor, then even though this is a weak interaction, it can compete with other reaction, and it may be that that's what Schwartz is seeing, although I haven't calculated that. Now, these are equations one must solve, and I must admit that we don't know how to solve this exactly in a continuum three-charge program. This program is important for atomic physics and many branches of physics, but we do not know how to solve this equation yet. It's a simple three-body Schrödinger equation with a three pairwise interacting Coulomb forces. The reason why we cannot solve is that we do not know theoretically all of the asymptotic behavior of wave functions in different phase-space factors. We are trying to solve this in our group, and eventually we'll probably be successful. But meanwhile, we looked at the approximate solution. For instance, in this case, you have to calculate the quantum scattering state, three-body quantum scattering state, and that's the equation you have solved. It looks so simple, but if you try to solve this exactly, you don't know how to do it because you don't know the asymptotic form. So we make an approximation of this equation for particular energy sectors and try to get an approximate solution. Normally, that type of solution equation is solved with what we call adiabatic approximation, where the electron velocity is much faster than the other two protons. Okay, but what happens if you have a different situation where electron is slow compared to one proton and the other proton is moving about? Then we found a solution where you can cancel gamma factor. And if that happens, continuum electron catalyzed fusion can occur. And the conditions are listed here. Many possibilities. Some of them may be applicable to some of the transmutation, but not all of them. Now I come to another concept or theoretical approach, and that is to look at Bohr's Einstein condensation, all the deuterium, not the atoms. This is for the rubidium atom, the famous data by Carl Wieman, published a couple of years ago. And for Bohr's condensation, what we are talking about is essentially trying to cool the system so that all of these particles go to the lowest state. And of course, the Einstein's prediction is that it will form a condensate which behaves like one particle. And the question is, can this occur with deuterium? Now, there are certain criteria you have to satisfy to have deuterium boson Einstein condensate. And this is a requirement that this wavelength of each particle has to have a certain length which will fit the density of the collection of deuterium. And if you work this out for the deuterium, you have this condition for velocity of C. That is, all of the deuterium has to have this order of magnitude velocity to have condensate. So the relative velocity, if you convert the meter second into 12 meter second, it's a really slow deuterium. So you could ask, how could you have condensate, and how could you achieve that? And it's not the entire story, because what it matters is the relative velocity between deuterium. If you can make a system of the deuterium which moves together in a certain direction by some means, and if relative velocity among them is low, then you have an effectively low temperature. Instantly, the Maxwellian distribution breaks up, and what matters is this guy. And so if you translate this as a temperature, you're talking about this kind of temperature, but that's among the deuterium which is moving, not looking in lab system. And another requirement is time scale. You can't violate the uncertainty principle, so the lifetime of the condensate has to be longer than that. Otherwise, condensate will not exist. Okay, now, what are possible way to get that? And I admit this is a speculation, but I want you to think about and maybe achieve experimentally. In the cold fusion measurement, there are lots of bubbles in the cathode and lots of microcavity. So that's the ideal place to track deuterium, substantial number. Even though it's a microcavity, you could trap thousands or 10,000 deuterium molecule, and analyzing them, you might have a deuterium plasma. And if they start moving together in a certain direction or oscillate, that's the condition you need. I don't know how to do it myself, but I want you to think about it if you experiment with it. So key is to have this, this condition. This may be difficult, but in cold fusion type experiment, there are millions of bubbles in the system, and if only one of them, or maybe thousands of them, attain this type of condition, then you have it. Now, what's the consequence of deuterium condensate? See, the condensate acts like a one particle. So tail of the deuterium which fuses will go off as a helium core. But the condensate, rest of the condensate, will behave like another particle. So they will absorb the the default energy. So there won't be any more gamma radiation that happens. Okay? And furthermore, this is very important. This process is a strong interaction process, not even for plus gamma. That's an electromagnetic process, so it's a million times smaller. But this strong interaction process should be larger than conventional process because of the large overlap. We know this from theoretical calculation. Helium for crushed wave function. So this might offer another mechanism for radiation-less fusion, but higher than this conventional fusion. So you will see this, but you don't see that because that dominates. Very interesting speculation. Now I come to Hasagi's experiment, and we have seen all this before. Palladium has a 250 electron volt spring energy. This palladium oxide has a 600 electron. I think this comes out to be savior of Bohr fusion. I think it's that important to independently confirm it. Because if it's a 600 electron volt, you can have almost original plane of plasma tone, but of course you may not have such a smooth scaling down to zero energy. That to be investigated. But the fact that you can get this kind of screen at 2.5 kBe is really encouraging result. And even if it's a 250 electron volt for the palladium itself, this could be a little bit smaller, maybe Jones level. So maybe that's what's happening. That is very low level, indeed fusion is happening. My own interpretation of this data is that essentially this continuum electron catalyzed fusion from deuterium plasmas. And it looked like if you pull the target and use oxide, which has slower diffusion coefficient for deuterium, maybe you can efficiently trap the deuterium to the high concentration, and then having some electron do the continuum electron catalyzed fusion can essentially bring that spring energy to higher level. But what that means is that this may not scale for each case. It's not universal constant, dependent on system. And this is suggested experiment tested in addition to the independent test of the linear experiment. If you're doing this type of experiment, I suggest to bring the electron in and see whether you can see either enhance or decrease cross-section by doing this experiment. Now, the simple prediction I will show you schematically would be this. If continuum electron is playing a role, then doing this experiment, you can plot your yield of cross-section and see whether it concentrates at the lower end. If this is observed, then it's a confirmation of our prediction. And as I said before, we may not have just simple scaling like that. If it's a continuum electron screen dynamical modification, not the static modification, so that the effect may depend upon system and other physical conditions. And of course that may fit into many of the experiments which give diverse different results. Okay. I'm checking whether you're giving a full time. You're honest. As I always think. Anyway, these statement I just made, you know, this is the most important point of opposition, theoretical opposition. And I'm saying it's not rigorous and it's not universal. Depends upon system. Okay? And another thing is, I give an example of that. Theoretically and experimentally, this can be tested. If you have a continuum electron, I've shown that a particular energy sector, you can have gamma factor cancellation. And this is very intriguing possibility because you can have a radiation with gamma. And this final statement I'm making is so important to us. See, all the criticism we get from anti-Bohr fusion people is already showing me reproducible experiment. And indeed, we have to really address this. No theory works until this is done. And the Kazaki type experiment may remedy this situation. Thank you, Your Honor.
I would say that even though you didn't acknowledge it so clearly, your neck is stuck out too. Do we have any questions or comments? So let me conclude the session by thanking the speakers for the ideal talks and the audience for the criticism and comments.